Huang, and she's going to speak about the existence of static vacuum metrics with prescribed Bartnik boundary data. Please.
I have to turn it on. It's a great pleasure to be in Toronto for the first time. What a beautiful city and the campus. And also thank Christina in particular. And I also apologize for just arriving yesterday because I was virtual for some of the first few days and it was very difficult to get away because of teaching, right? But I enjoy all the talks online or here. So let me tell you what kind of problem we want to work on. So some of them already mentioned in the talks this morning. So if we think about, say, we have S2 and we have a Riemannian matrix. Let's see, I used tau and a scalar function. And the goal really is to find an Riemannian matrix, which I'm going to define where the Riemannian matrix lives, goes to the Euclidean, and the scalar function u goes to 1 R3 over removable at infinity. So this is Riemannian matrix, and this is scalar function. Such that G and U satisfy the following boundary value problem. And here, this my notation. So here is the matrix G and U defined on the exterior of R3, and these are the boundary value on the boundary of a manifold. Right. So in other words, you can think about this is a prescribed boundary value problem. Give a tau and phi, we want to find a solution such as G with some asymptoticity at infinity, then you satisfy this interior equation and the boundary value equation. So the interior equation, let me denote by SGU, is usually called a static vacuum equation. So this tells you, you want to say, okay, can we prescribe the boundary value of static vacuum matrix? And this is usually called, these two quantities together, as in the talk this morning, it's called the Bartnik boundary data. So if I only have 5 minutes, then I'm happy to done with here because you know what the content in my title. We want to solve this equation with the boundary value problem. So what are the examples of the solution? Okay, so before looking at examples, why people are interested in static vacuum matrix G and U, because it really has some motivation comes from relativity. So in the case where U is positive, so there I don't require U to be have a sign for the statement, but if U is positive, then you can consider the warp product matrix. Right, with either plus or minus sign, or even or equivalently, you get either Riemannian matrix or Lorentzian matrix. This matrix is Ricci flat. Right, so if the Lorentzian matrix, that tells you it's a solution to the Einstein equation. So let's look at some examples of static vacuum matrix. Okay, so a very special case, but a very large class is when you take U to be constant or U equal to 1, and then all the Ricci flat matrix. can be put in this bigger class of static vacuum matrix. But there are more. So here in this talk, we'll particularly restrict to asymptotically flat. And it's conveniently has been defined in this morning's talks. So we're looking at asymptotic flat, static vacuum. Then we have the Euclidean matrix. In particular, it's a rigid flat matrix. And there's also a class of so-called the Schwarzschild family, which has also been mentioned in morning's talks. So I think I could write here. I have enough space here. Right, so here I'm talking about the slice in the space-time. So that's a Riemannian Schwarzschild manifold with the mass m. So it's actually a family of manifolds parametrized by real number m. It's also called the ADM mass. And if you write down the matrix, so there are different ways to write it, but you can write in this following form, like using the spherical coordinates. Okay, and here Gn is the matrix that's static with the function, usually also called the static potential, defined by this quantity. Okay, so this matrix has very interesting property. As a first example of black hole, existence of black hole by this model. And if you're looking at, this is rotationally symmetric matrix. So I suppress the dimension. Let's think about this is like two-dimensional Schwarzschild, right? Although everything I say is have so far n dimension. Do I have n? Yeah, n here. The dimension is greater or equal to 3. Dimension of all those manifolds I consider is greater or equal to 3. So if you draw the schematic picture of Schwarzschild, it's rotationally symmetric, and this is the asymptotic flat end. And there's singularity of this term in the matrix, right? So if n is positive, then the matrix will become negative somewhere. So this vector u will no longer define in the square root. But then where it becomes 0, so the 0 set of this function is a minima surface, and that's usually called the boundary of the black hole, or it's called the horizon. Okay, and there's a theorem of uniqueness of static black hole. So this theorem goes back to 60s and has been improved further on by many people. And so, for example, I think it's probably Israel or Robinson. So like a Bondi Masu Alam. So it depends, like there's some extra assumptions being generalized into the following statement I'm going to write. There's also work by the speaker Ponzi this morning. This direction. So the statement says, right? So this tells you the only static matrix which has a minimum surface boundary must be Schwarzschild. So if you want to super rigorous, that's possibly there's dimension of n less equal to 7, because the proof, one proof also used the positive mass theorem. Okay. All right. But this kind of contradicts to what we want to show, right? We want to show somehow you have a large freedom to prescribe the boundary value. In particular, we want to prescribe the induced matrix. I think I didn't really mention my notation of this G of T means the induced matrix. So it contradicts in some way, like it tells you if you have phi equal to 0, and then the matrix must be, the static vacuum matrix must be Schwarzschild, that tells you the induced matrix must be round, right? Please. It's only for positive, right? So only when positive mass, you will get a minimal surface boundary. I think probably there will be a talk about ZAS, right? This, like, to my understanding, is the case when you have negative mass, and then you will have a singularity, 1 point singularity. Yeah. Huh? You are giving the talk. So you will explain more to us. Thank you for asking. Right, but this, because with the minimal hypersurface boundary, that's only cover the positive mass. Right? So now you make us really look forward to your talk. So it kind of, there's contradiction in some way, right? But to solve this, we need to impose some condition, and that's actually the content of conjecture due to Bartnik. Please. Please.
So, I mean, I know full well that if you don't have any additional matter, then your Schwarzschild or whatever are the unique solutions. What's the minimal hypersurface boundary property?
Could you please say again your question?
I'm asking why have you added that statement, that minimal hypersurface boundary?
So you mean there's something without the minimal hypersurface boundary?
Well, I mean, is that just as a consequence of the Schwarzschild?
It's
the horizon.
Sorry?
It's the horizon.
I know, but I mean, is that an assumption, that minimal hypersurface boundary going in, or is it? I mean, because it's a consequence.
It's a consequence, right? I see what you mean. So let me answer from what I understand. Like the original statement says you assume U is 0 on the boundary, so that's part of the assumption, right? But U is 0 on the boundary imply the boundary has to be minimal surfaces. And the later work show you don't care about what U behave there. You just assume it's a minimal surface. And then
the reason for me being puzzled is that if you just allow yourself to have a sort of hyperspherical. Oh, but you don't assume. I see.
We don't assume symmetry. Yeah. So Birkhoff's theorem tells you rotational symmetry, a vacuum matrix must be Schwarzschild, right? But the point is here, we don't assume any symmetry, but assume it's static vacuum. Yeah. Thank you. Okay. Right, yeah, very good point. So if Schwarzschild will be include, so mass is 0 is Schwarzschild. Right, so I should say, so the statement is the only Schwarzschild with minimal hypersurface boundary has to be Schwarzschild. If it doesn't have boundary, then it must be Euclidean. If it doesn't have minimal surface boundary, then it has to be Euclidean. Okay, all right, so the Bartnik's vacuum extension conjecture related to the Bartnik's quasi-local mass, which has also been mentioned in the morning. So the whole program is roughly started this 89, and really what the statement says is under some condition, then the static vacuum extension G and U exist. So originally he conjectured for 3-dimensional manifold. So suppose we have a Riemannian matrix on a ball with boundary. So it's a topological diffeomorphic to a ball. So topological ball. And suppose it's a terrible bad drawing, doesn't look like a ball, but just think about it's a ball and the boundary is S2. Right? And then we have a matrix defined on the ball, which has non-negative scalar curvature. And also we have the mean curvature of the boundary to be greater or equal to 0. So this is mean curvature. Right, and then he can actually it can be, I think, weakened, so can be weakened to positive somewhere. Okay, then there exists let me call this geometric boundary value problem with a name. So I call the whole thing interior and the boundary equation to be this capital G U. And he conjecture say there is a static vacuum extension with that prescribed boundary where tau and phi equal to the induced Bartnik boundary data from the interior matrix. All right, so let's talk about why we will need this assumption there, right? So if the mean curvature is negative everywhere, suppose you have an extension. Right there, but if the mean curvature here is negative everywhere, or strictly negative, but then because the matrix goes to Euclidean, so over the large coordinate sphere, it has positive mean curvature. But so this is a barrier condition. We guarantee a minima surface will exist in between, right? So you will get a minima surface somewhere. It's 0. But then by the uniqueness static black hole, it tells you, oh, the exterior has to be Schwarzschild. But then the static matrix is actually analytic. So this is static, right? So that means it coincides everywhere. So that's we must start with the Schwarzschild data. But that tells you cannot prescribe this arbitrarily. Okay. So this comes from his program of quasi-local mass. If I have time, I can talk about at the end of school, end of lecture, end of the conference too. I'm staying Friday night. Then the second part is it also can be think about from a different point of view. Is here you are really looking at the isometric embedding problem with prescribed mean curvature, right? So now you give a matrix on the S2, give a function there. You want to say it can be isometric embedded into a static vacuum space-time. So here it tells you, okay, there is some condition of tau and phi which guarantee you can isometric into a static vacuum space-time. And for the isometric embedding into static vacuum space-time, it also be used by Morgov. So they don't use this result, but they assume there's isometric embedding. So that's by Poning, Chen, Udao, Huang, and Yao. They have the definition of quasi-local mass with the reference matrix to be static vacuum. A different approach of Bartnik's quasi-local mass. Okay. But this conjecture also people tend to believe in this most general form may not be quite right. There's a conjecture counterexample. By Michael Anderson. So this kind of example probably already appeared in Curie, but the conjecture was formulated in the paper of Anderson, Jerge. So this is so the example actually failed this conjecture in a very unexpected way. Is if you're looking at just R3 with the Euclidean matrix, right? And then you want to have a ball with some interior matrix, and you take just be Euclidean, but then you take a ball which doesn't really look like a ball in R3. So it's a really thin hula loop shape, and which you can guarantee the mean curvature of this respect to Euclidean matrix is positive. Okay, so it's a mean curvature is positive actually everywhere this region. We call this omega, but omega is also topological diffeomorphic to a ball, and the boundary is diffeomorphic to S2, right? So you can take induce, you actually make it touch in case you don't see it's touch. So this not embedded, not outer embedded. And then you take the induced data from this, just from the Euclidean. And you take the data, now you can plug it into your boundary value problem, and you ask whether there will be an extension. A natural solution would be, well, you just take everything to be Euclidean inside, right? How about just take a Euclidean matrix to be the extension? But the problem still in the very delicate way is it actually, this region is not amenable with boundary. Right, so this is not a valid solution to your boundary value problem. Now the question is, do you have other possible extension, not the Euclidean matrix? It's not known. Okay, but nevertheless, it still be interesting to understand. Well, probably you have to impose some additional condition to say you can actually find the static vacuum matrix, because as I told you, those examples, essentially that's the examples we know the exact solution about static vacuum matrix, right? So it looks very rigid, but then this tells you there's also some flexibility of finding static vacuum matrix. Okay, so what we want to study is really looking at the so-called local well-posedness conjecture. This PDE is very nonlinear just because you have the Ricci curvature there. It's a nonlinear equation in G. So this conjecture essentially says a global well-posedness, right? You want to say given some tau and phi with some condition, you can find a solution. You also conjecture the solution is unique. Okay. But then how about let's looking at the local well-posedness first. So the local well-posedness will say if you have tau and phi, which you know already give you some solution, and then you want to be able to solve this equation for the nearby tau and phi. So if tau and phi already has a solution, that means we already have a background static vacuum matrix. Right? So I want to take, now let me take a n to be a general n dimension, and then I have a background static vacuum. So this is asymptotic flat, static vacuum, background matrix, background pair. Okay. And how about let me use this picture. So suppose this is our background. Now it can be complete like a Rn, Euclidean, or it can have a boundary. And how do we choose tau and phi? We're actually thinking about that will be the induced data of the hypersurface inside. So we'll have a hypersurface here, and which are the boundary of some region omega. So this will be the hypersurface. So to be more specific, I want omega to be a bounded open subset n, and such that n include the boundary if the boundary is not empty. Okay, and then I let sigma. So also I let this the complement of omega to be connected. So really I'm looking at only one asymptotic flat end. And I call the boundary of this that embedded hypersurface called sigma. So this is embedded. Okay. All right. So now we want to looking at the Bartnik data induced from sigma. Right, and which I know there's already a solution, G bar, U bar. So now I let tau and phi close in some suitable space. Right, and the conjecture would say, the reasonable conjecture says, will be there exist or a solution G and U, which is asymptotic flat. In the sense, G goes to the Euclidean matrix and U goes to 1 at infinity, such that. And also, well, I want to use this equation, but for more general setting, right? So this question really, if I compare to my statement of local Wilpo's conjecture, that's when this is n minus sigma, and this is sigma. Sorry, what I say, n minus omega, right? And that's the boundary. Why not? If we can prove more general than this topology, let's do it. So we have, right, and now it can be also general dimension. So this will be, and we clean the board here, and this will be, right. So we can just generalize the question to more possible underlying manifolds before more general than what originally stated. Right. So this says for Lat operator T, you will satisfy static. So the first two equations is 0, and then the boundary data will be the arbitrary tau and phi you prescribe here. And also a reasonable conjecture to put inside here is it has to be locally unique. So the G and U is unique, at least for if you consider solutions which are close to the background one. And also you can say it has to vary smoothly in the boundary data you input. So, but this is very smoothly. In the boundary data tau and phi. So the smooth dependence. Okay. Okay. Let me pause for if you have any questions. Okay. So there is some results for this local Wilpo's conjecture. One of the very first work is by Chen. Yeah. He proved that this local Wilpo's conjecture true if the background is Euclidean and 3-dimension, and the boundary is a round sphere. and also this tau and phi satisfy the refractional symmetry. In other words, if you have tau and phi, which is very close to the round matrix and to the mean curvature of the round sphere in R3, and you've also satisfied the refractional symmetry, and he showed the existence of static vacuum extension. There's also later the work of across, I believe, is the 3 planes, 3 like x, y, y, z.
Okay.
All 3 planes. And the work of Anderson, Curry, they showed this boundary value problem, although just like you look at the Ricci equation, it's not naturally elliptic, right? But they can say under some suitable gauge, they actually look at the space-time matrix and look at the harmonic gauge for the space-time matrix. And they show it's an elliptic boundary value problem. And also compute index. So it's a fraction of index 0. And based on this foundational work, Anderson claimed he can remove the reflectional symmetry in Miao's work. Probably also, let me mention there's some numerical results by Kala, Sedabon, Renee, and Stritlaw. Under the boundary data is axiosymmetric. Okay. So I think we can talk about our theorem. Everything I say here is talking joint work with Zhongshan N. So it's based on the result on 2 papers. Let me write down the archive number. So the first paper is already appeared in Cambridge Journal of Mathematics, and second one we posted earlier this year. Roughly, we say the local Wilpo's conjecture holds for a large class of hypersurfaces. Right, so in the first paper, we consider the background is Euclidean. And in the Euclidean matrix, you can actually take advantage, it's Ricci flat. So there are a lot of really amazing phenomena happen when you take a Euclidean background matrix. In that case, we can show any, so this is Euclidean. And we show any star shape hypersurfaces. Star. Right, so star shape means it really somehow look like, well, I mean, we need to assume it's smooth, so it's a smooth star. I cannot draw a star here, but it's something like a, how about round it off? I hope this is star shape. So of course, it includes all the convex hypersurfaces. And then in the second paper, we extend our framework to the general static vacuum background. Like for example, include Schwarzschild, and our result is say for a generic hypersurface inside that general static vacuum background, the well-posed conjecture, well-posedness conjecture holds. And there's a condition we really don't like, but so far we need to put this assumption, is the hypersurface has to be analytic. So in fact, we show there's an open dense set of the hypersurfaces, and you can pick it, and then you can look at the induced data from on that hypersurface, and then the local well-posed conjecture true for that induced boundary data. Let me use this one. Some remark. I have until like a 15 to 15 to 20. Oh, okay. I have plenty of time. Good. So remark is we can remove this we don't like condition analytic for the Euclidean background. And also it can be localized in the sense we just need a piece of the hypersurface to be analytic. But I will not go into that detail, but also I think I forgot to mention one additional condition, topological condition we need to put for the second class of hypersurfaces. So we need to require the hypersurface has this condition. So this relative first fundamental group of sigma as a subset in the exterior has to be trivial. So this condition means the fundamental group sigma is actually bigger than the fundamental group of the exterior. Right, so this map by the induced from the inclusion is surjective, right? But notice, so in particular, if the exterior has trivial topology, then it's always true, right? So, and in fact, we don't really know in our limited knowledge about the exact solution of a static matrix. We don't really know anything which this condition doesn't hold. But just for our technique, we need to input that, use that assumption. Okay, and what the generic means we're really looking at family of surfaces sigma t. So you can think about foliation, but also we can prove more general than foliation. For example, they can touch each other in some suitable way. But you can just think about it as a foliation. Okay. And then, so here is where the parameter t goes from epsilon to epsilon, right? And then we can find an open dense subset for the range of t. Such that for any number inside this open dense set, then sigma a, the local well-posed conjecture holds for A. So that's what open dense means, generic means. So I think I have time to talk about some proof, if you allow me to say some proof. So what very fundamental fact we use, this is indeed after suitable gauge, is a Fredholm of index 0. So just like you learn in PDE course, if you want to solve harmonic function And if threshold index 0, you want to show the kernel is trivial, right? And then you can show the operator is surjective. So understanding the kernel of this problem is very important. So what would be the possible kernel? But just like all geometric problem, diffeomorphism naturally give you a lot of solution. You have a G and U, which as a metric tensor, you write down in some particular form. It's one solution to the PD. But then you introduce diffeomorphism, you get another solution which look like a totally different symmetry to tensor, but it's still a solution, right? So what's the diffeomorphism group for this problem? And I think somehow it's less well understood in the literature. And we find out the diffeomorphism group, which should be taken into account of this problem, is all those diffeomorphism. So you expect the diffeomorphism to fix the boundary, right? Because you are looking at the boundary value problem. So on the boundary has to be identity, but you also say, how about let's fix the infinity of a diffeomorphism to be the identity? Somehow it's not enough, because for the asymptotic flat matrix, there's a natural class so-called structure at infinity, which you can rotate, you can translate, then it's still a valid solution. So at infinity, we have to take into account this translation rotation. Okay, so then for this class of diffeomorphism, now you take the background one, and then you pull back by the diffeomorphism. And you plug in back into the equation, it's going to satisfy the same boundary value problem. So in other words, if you consider a family of phi t inside your diffeomorphism group, and then you differentiate in T, you can, right? So that will correspond to you took a tangent space of this diffeomorphism group. And that's called a vector field, space of vector field, which is just a differential, the tangent space at identity map of the, okay? And then that will tell you the linearized problem. And then when you linearize your chain rule, you have a linearized problem, linearized operator for T, and then you have a differentiation inside. And the right-hand side does not depend on T, so it's 0. So that tells you all those elements are in your kernel. I don't know if you can see, let me pull it up. But the space X is just any vector field on the exterior region, such as X is 0 on the boundary, and X goes like a rotation and translation. So it's an infinite dimensional space. Right. So our first ingredients toward the general theorem, which I don't know where is it now. Is it here? Okay. We show that although the kernel space is very large, gigantic, but we show if that's the only kernel element of the linearized problem, then the local well-posed conjecture holds. Okay, and then there's two other theorems. Let me probably just write it down, and then we can finish there. And then, so now you want to see for what kind of hypersurfaces the kernel of the linearized problem is trivial in this sense, right? And we introduce a static. The local well-posed conjecture holds. Yeah.
Yeah. Just the sentence was, I mean, is trivial, right?
It's trivial in the sense equal.
Okay, it's equal to that. Okay.
Right, it's no more than that. Right, so here we show all those elements are in the kernel, but it could be bigger. Yeah, thank you. Okay, so, and the second one is we show there's a condition that we define, it's called static regular, which I will not, I don't have time to talk about it. So it's a really global condition, it's not locally the hypersurface sigma. Then the kernel equals and now the theorem B to conclude that our theorem some way was just show those. Did I erase it already? Okay, so yeah, that's here. So for those two class of surfaces we consider, they are static regular. So then that will complete this theorem. Okay. Okay, I think that's enough time. Yeah, thank you.